Hi, I'm Dr. Miguel Mitchell, founder of ChemAnimation.com. Welcome to the first in a series of lectures on natural product synthesis. Our first topic is biomimetic synthesis involving cationic cyclization. I'll explain what this complicated title means after I explain what natural products are. First thing we have to consider is, what are natural products? Natural products are organic compounds made as secondary metabolites by a wide variety of organisms, including plants, animals, and microbes. Secondary metabolites aren't protein, fat, carbohydrates, DNA, or RNA. These are needed for everyday survival. Secondary metabolites help the organism to survive better. These survival advantages can be conferred in a number of ways. As toxins, the natural product can kill prey or defend against predators. Antimicrobial natural products act as a chemical immune system, fighting infection. To propagate the species, a natural product may be a pheromone, a sex attractant produced by a female to attract a male. And as repellents, such as the odor in a skunk's spray, a natural product can repel a potential predator. One of the side benefits of natural products is that they represent 60% of all FDA-approved drugs, including those that treat heart disease, infections, and cancer. Now that we've covered what natural products are, let's go back to the lecture title, Biomimetic Synthesis Involving Cationic Cyclization, which is a real mouthful. Biomimetic synthesis is using organic reactions to copy or mimic how organisms make natural products. Cationic cyclization is making a ring by a carbocation grabbing the electrons from a lone pair or pi bond tethered to it. For example, a protonated epoxide can act as a masked carbocation. Its electron sink will pull electrons from a nearby tethered pi bond to make a ring. Relief of ring strain from the epoxide opening drives the process. As a common example of biomimetic synthesis involving cationic cyclization, let's take a look at the cyclic terpenes. Terpenes are natural products derived from 5-carbon isoprene units. Biologically, all terpenes are made from two 5-carbon isomers, dimethylallyl pyrophosphate or DMAPP, and isopentenyl pyrophosphate or IPP, which are coupled together with enzymes. The smallest terpene, monoterpenes, are made from 2 isoprene units or 10 carbons. Sesquiterpenes contain 15 carbons or the linkage of 3 isoprene units. Diterpenes, 20 carbons, are derived from 4 coupled isoprene units. And there are higher terpenes, triterpenes with 30 carbons, and even larger structures whose skeletons are all made from linked isoprene units. Here is our first example of the mechanism of cationic cyclization to prepare a terpene. An electrophile E+ attaches to the lone pair of an epoxide, activating it for ring opening. In a concerted or simultaneous process, the epoxide ring opens as electrons from the nearby pi bond flow toward it, and simultaneously the development of positive charge in the reacting pi bond pulls electron density from the next pi bond. Note the chair-like transition state that produces the lowest energy path for the cyclization and enforces extremely high stereoselectivity, which is why only one diastereomer forms. In our second example of cationic cyclization, here we have a strained bicyclic ring. Protonation of the oxygen creates a strong electron sink near the adjacent pi bond, which simultaneously pulls electron density from the tethered pi bond to make the new ring. The anion A- then attaches to the final carbocation, ending the process. Why is the isopropyl group cis to the R2 group? To avoid pointing to the more sterically hindered bottom of the larger ring, the isopropyl group points up, or exo, making it cis to the R2 group. Okay, now to figure out how to synthesize a cyclic terpene, we can use our cationic cyclization strategy in retrosynthetic analysis, or working backwards from our target cyclic terpene. In the top example, we first have to see that the OH used to be part of a strained bicyclic ring. in which the oxygen atom was once connected to the alkene carbon with the R group. If you mentally flow the electrons backwards, the lone pair on the oxygen to the alkene pi bond, then to the carbon-carbon sigma bond, make a pi bond while breaking the sigma bond, and then make a pi bond while kicking out A-, you have successfully reversed the process. In the bottom example, the OH was once part of an epoxide, and pushing the electrons backwards, reforming the epoxide, pushes electrons toward the ring junction, forming a pi bond and breaking a carbon-carbon sigma bond, at which point the electrons kick out A- to make a pi bond and bring you to a reactant. Now it's your turn to propose a synthetic route, working backwards from the monoterpene Balanitol to a starting material with 7 or fewer carbons. As a hint, remember from first-year organic chemistry that, as one way to alkylate a carbon skeleton, you can react a primary alkyl halide with enolate anion, but you have to work backwards to C double bond O first. Good luck! Here's the answer to the practice problem. First, remove the hydrogen shown in red to work back to the correctly positioned alkene. Now, revert to the starting material by having the oxygen lone pair reform a bicyclic ring, pushing the pi electrons to reposition the pi bond, which flows the electrons toward OH, remaking a pi bond and displacing OH. Aqueous acid would do the job of inducing cationic cyclization in the forward direction. Now the alkene came from a ketone, so use Wittig olefination to accomplish this. You need the ketone to figure out how to attach the two alkyl groups. First, disconnect methyl, because you want the last alkyl group to be in the less sterically hindered exo face. LDA or another strong non-nucleophilic base would yield the enolate, which reacts with methyl halide or sulfonate. The last step in the retrosynthesis is the same as the former. Just replace the methyl halide or sulfonate with homoallylic halide or sulfonate. On this slide are shown the reference and the details of the published synthesis.